Alright, this podcast that I'm doing is dealing with section 8.6 in our textbook on the Pythagorean Theorem. What I want to do for you guys here is just illustrate the Pythagorean Theorem and then run through one of the more famous proofs of it. Now here in Sketchpad I already have this drawn and it should look a little familiar to you because I've got something that pretty much looks like this on a poster in front of my classroom. If you guys remember back to Algebra 1, it's the first time you saw the Pythagorean Theorem. Everyone kind of knows it's a squared plus b squared equals c squared, but you may not know what that really means. And actually, this diagram is going to kind of hopefully clarify it a little bit. Because actually, in some countries, the Pythagorean theorem is called the theorem of three squares. Here's my three squares. Because what I did here, I've got a right triangle. My legs are length A and B. My hypotenuse is C. And what I did on each of these little sides here, I constructed a square that has each of those as a given length. So again, square on the left here, all the sides are A. Square on the bottom here, all the sides are length B. Square up here is all length C. And then if you remember, the area of a square is just the length of one of the sides squared. So this is A squared, this is B squared, this is C squared. So if you follow the Pythagorean theorem, if I take the area of this square on the left plus the area of the square on the bottom, I should get the area of the square on top. And when I actually measured the areas in Sketchpad, that's what I got. This one up here, this one right here, this is my area of my small one, which right now is 4.83 square centimeters. The one below it is the area of the bottom square, which is 24.54 square centimeters. And the area of the big one is 29.37, which is coincidentally what I get when I add the two small ones together. And it'll always stay that way. I can manipulate this a little bit. I can make this bigger, make this smaller, but these two areas will always add up to be that area. And this is one of the things the ancient Greeks used a lot when they did something called quadrature, which is actually, I find interesting. I don't know if you guys would, but might be something worth looking at on the internet. The other question I kind of had, if you're interested in a little bit of extra credit here, is I'm just wondering if the Pythagorean theorem or something like this would hold if this wasn't a right triangle. If I actually, say, instead of putting a right triangle, you had an obtuse triangle or an acute triangle and constructed the squares on the sides. Or if maybe instead of constructing squares on this right triangle, maybe I put like a semicircle on here or an equilateral triangle or something. Just curious whether the areas would be the same. Someone can show me whether they are or not. There might be a few points in there for you. Okay, now the proof. Here's what the proof looks like. There's several proofs of Pythagorean theorem, but this is probably one of the easier ones to grasp. What I've done here is I took a right triangle where the legs again are A and B and the hypotenuse is C. Took 4 copies of them and laid them out like this so that the outside border here makes a square, and then I got a square on the inside. So I got a big square and I got a small square. And the proof of the Pythagorean theorem here is actually dealing with the areas of the two squares. Because the area of the small square, this one that I've already colored in yellow, it's pretty easy to figure out. If the length of each of the sides is C, okay, then the area is C squared, isn't it? Alright, and the area of the big square, well, we need to know the length of the side. And each of these sides, if you see I got an A and a B, an A and a B, an A and a B, and an A and a B, each one is A plus B units long. Okay. Now the proof is what we need to do is we take the area of the big square, which is right here. The area again is like length times width, or one of the lengths of the side squared, which is A plus B times A plus B. You have to FOIL this thing out. You get the area of the big square being A squared plus 2AB plus B squared. Okay. And the area of the little square, which is right here, we've already taken care of. That's C squared. But is that the only way to actually figure out the area of this little square here? Because a different way of actually figuring out that area of the little square is by taking the area of this big square and then subtracting the areas of each of these 4 rectangles out of that big square, and that would leave us with what's left on the inside here. So showing that a little bit, okay, the area of the little square equals the area of the big square minus 4 right triangles. Okay, this right here again is what we had figured out as the area of the big square, the a squared plus 2ab plus b squared. The thing I've got right next to it is the area of the 4 right triangles. The 4 on the outside, is there because I've got 4 triangles. Each of the triangles, the area is 1/2 times a times b. Because you look here, the base you could think of as either a or b, and the height would be the other one. So 1/2 times a times b would get you one of these. Multiply it by 4, that will get you the area of all 4 of them. Okay, back to here. Well, 4 times 1/2 is 2. So simplifying this a little bit, again, here's my big square. My little square is the minus 2ab part. But if I simplify that, I've got a plus 2ab and a minus 2ab. They cancel out. I'm left with a squared plus b squared. So the area of my little square was a squared plus b squared. But up here, I already figured out the area of the little square was c squared. So you know what? That means they got to be the same thing. So a squared plus b squared has to be equal to c squared. So there's a proof of the Pythagorean theorem. Isn't that nifty? I like it. I love proofs. I know you guys love proofs.